that's how you pull out performance, right? You don't just know one aspect and then like leave the rest to chance. No, you know everything you can about everything about your system in order to tweak the knobs in the right places in order to do like the incredible, something that's never been done. And that's the only way. Like you need to know everything.
AyJay, thanks for joining me.
Thanks.
Really excited.
Thanks for having me.
Yeah, first run through the new setup back here.
I mean, it's beautiful in here.
Yeah.
I wish my house had this much natural light.
It does help to have one huge window.
That probably helps a little bit, yeah.
Sweet. So I guess to start things off, let's like place, who you are and what you're working on. So maybe you can just tell us about what Albedo does and go a bit into like how you came to that, what your background is.
Yeah. So I'm co-founder CTO at Albedo, where we're building ultra high resolution imaging satellites to collect the same level of quality you would get from planes and drones. But we're flying in this new orbital regime called very low Earth orbit. So there's a lot of satellites in low Earth orbit. That's typically where like Starlinks are launched into. We're even closer than that. And what that allows us to do is to take, rather than a very, very, very big camera that you would need to collect drone quality imagery from space, something like the size of a school bus, you fly closer to the Earth, you shrink it down quite a lot, and now you've got a much cheaper, much easier to build system that's getting the same resolution from a pretty interesting orbit.
And what had you been doing? Like what set you up to build such a thing?
Yeah, I was kind of into space starting in third grade. My third grade teacher took us all out, did that experiment where you take a 2-liter bottle and you fill it up a little bit with water, and then you put it on a bike pump and you pump it and it just shoots up. Kind of was like, oh my God, that's the most incredible thing I've ever seen in my life, because my life wasn't that long at that point. But from there, kind of wanted to be a rocket scientist. Always got infatuated with the term, well, it's not rocket science. And instead, I was like, well, I actually do want it to be rocket science. So I went through high school, was looking at colleges. Around the time I graduated high school was right after the 2008 financial crisis. So I was like, oh, I can't go out of state. I gotta try and save money, and I gotta get a good job. So I ended up going to Colorado School of Mines because I grew up in Denver. Great school, doesn't have an aerospace program. So instead I was like, well, if I'm gonna build rockets, maybe I'll do mechanical engineering. So went through mechanical engineering, then started looking for jobs, applied to the only rocket company I knew at that time because SpaceX was just starting to be a thing, which was ULA, United Launch Alliance. They didn't have any jobs. So I was like, well, ULA is this joint venture between Boeing and Lockheed, and turns out Lockheed was also in Colorado. Got a job at Lockheed, but ended up working on satellites instead of rockets because turns out Lockheed doesn't build rockets. That's what ULA does. And then got kind of like swooped into this whole classified world of working on government satellites prior to starting Albedo.
Sweet. And then, so what was the genesis of the idea behind Albedo? Like, how did you decide? I guess there's a bunch of different strands. Like one is like, can we do higher resolution Earth observation? But also, certainly I imagine there's a point where you asked yourself, can we fly in VLEO? Yeah.
So I've got two other co-founders, Topher Haddad and Winston Tree. And Topher and I worked at Lockheed together. Topher had the original idea for Albedo based off of a tweet from Trump of an Iranian missile site. Looked like it was about 10 centimeters. And then they talked about this tweet at a conference called World Satellite Business Week, where all the kind of commercial imagery leaders got together. And on that panel, somebody asked, would there be a market for 10 centimeter imagery? Everyone was like, yeah, absolutely. But it would cost $1 billion to build that satellite. And so Topher was like, well, no, knowing this concept about the distance from your target related to your overall aperture size, if we fly much closer to Earth, you don't need that school bus size satellite like I was talking about. And hey, what's this kind of new orbit called VLEO, very low Earth orbit? Lots of drag there. But there's been enough advances in technology recently, things like Hall effect thrusters, which basically are electric propulsion thrusters that rip ions off of atoms and shoot them out the back of your satellite to create super low thrust that can maintain your orbit. We should be able to do this. And so I heard through the grapevine pretty shortly after he had this idea from someone else at Lockheed who was like, did you hear Topher, like this is right around COVID, did you hear Topher's like thinking about quitting to start this startup? What an idiot. And I was like, haha, yeah, totally. Hey, Topher, what's this? And he's like, yeah, I actually wanted to talk to you. Can you come over Friday? So I went over to his place, gave me kind of the lowdown of the idea. And I was like, that's cool. Well, do you know how to build it? And he's like, no, that's why I wanted to talk to you. So he's like, I also have this friend I went to school with, and we lived together in SF. His name's Winston. He's currently at Facebook looking at imagery data. I think it'd be great to pull together. And so we got together just knowing that I had built so many different systems. I was a chief system architect at Lockheed before I quit. And so kind of that early design concept of like, here's all the pieces that need to come together in order for this to work. And then just knowing like, we're smart guys, we can figure out how to build a satellite pretty easy.
Yeah, like any pair of smart guys can do. Yeah, I don't know. I mean, oftentimes I like to talk through like what is hard about this, but like I feel like the punchline for flying a VLEO is like everything. Yeah. And so maybe we can go through it a little bit more chronologically and like how you approach and thought about it. Like, did you at that point, did you know, like, were you like, what, like, where were you at? Like, how did you think about breaking the problem down? Were you immediately a high conviction that this is something you could go execute, or did it feel like exploratory for a while?
Yeah. Well, it helped that I was a system architect before I quit Lockheed. So I had like experience of starting with this big ambiguous problem and then trying to chunk it down into these subsections of ways to solve it. And then you throw in VLEO, like this new orbit, but that's kind of the initial part of how you size and build a system. So from the get-go, you kind of look like, what are my like key requirements, we call them key requirements that the system needs to do. It needs to, we had a target for 10 centimeters. We knew that our aperture size, the size of like the opening of the telescope couldn't be very big because the cost of the system when you build satellites like this is typically, the rule of thumb is like cubed with the size of your aperture. And so like trying to keep that as small as possible, which means the smaller you go, the closer to the Earth you need to be. And so your orbit gets lower and lower. But as your orbit gets lower, your drag increases. And so
like in Topher's initial insight, was there actually work done on the rest of the how cost played out? Or it was just like, we have this basic rubric for how cost relates to aperture?
Basic rubric.
Okay.
Yeah.
Right.
Yeah. And like, I think at the time he was like, yeah, we can get down to like less than 20 million, maybe like target like 10 million a satellite. And if we can do this.
So you start with just a math equation of like aperture to like a price range that seems good. Yeah. And then you have to be like, how do we fly there? And maybe like a brief interlude, like what's going on in VLEO and why is no one else flying there?
Yeah. Yeah. One fun thing when I'm talking with people is not a ton of people think about orbits and like the rocket science behind like what is falling through space? What is gravity? How do you actually end up circular or going circular around any kind of like celestial body. So there's a lot of different orbit types that people typically think of. There's geosynchronous orbit, which is like you're really, really far out there. This is where like GPS sits, where some of our comms satellites sit, and they are orbiting at the same rate that the Earth is spinning. And so they're always looking at one spot on the Earth. And like that has a bunch of like radiation out there. It's really hard to get to. So that's its own fun. Then there's some orbits in between I won't bring up. But then as you get closer and closer to Earth, the like low Earth orbit, that's between like 500, 400 and like 1,000, 1,600 kilometers. In that orbit, like you're just inside the radiation belt that kind of like sits surrounding the Earth that is between LEO and GEO. And because you're there, there's a little bit of atmosphere. That's part of like what's kind of protecting you. And that atmosphere causes drag. It's one of the more like significant forces that are acting on you in addition to gravity as you're spinning around. But it's still not a lot. Like you can be in a LEO orbit and sit up there for like 25 years and like eventually drag will bring you down and you'll like deorbit and hit the Earth. In VLEO, you can think of like the atmosphere doesn't actually ever end. Like the air that we're breathing, it doesn't like hit a boundary and it's like, we're done. Instead,
it's not a discrete.
Yeah, it's not a discrete.
It's just like, orb encompassing there.
Atmosphere, no atmosphere. Yeah. Instead, it gets like less and less dense. And so as you go further away from the surface of the Earth, that density decreases to a point where like the definition of space is around that point where like planes, like jets can't really thrust anymore. You're not getting enough air density into your fuel air mixture to get propulsive thrust. And so past that point is what we call space. That's around like 100 kilometers. So VLEO is the point where you're still in that like less dense atmosphere, but it's still like significantly more dense than LEO, like I described, around like 400, 500 kilometers. And so what that means is now you're dealing with a lot more drag, a lot more significant force acting in the opposite direction of your orbital path, which means instead of spending like 25 years in orbit, at certain points in VLEO, you might only last like 5 days. At other points, like towards the top end, you might last like 2 months, but still like way, way shorter. Like if you're going to spend millions of dollars to build a satellite and then millions more to launch the satellite, you don't want it to like just be up there for like a couple weeks. Like who does that? So the fundamental kind of like assessment was, okay, we actually do have this kind of fun comparison between I'm going to spend 10 years and $2 billion to build a huge, massive school bus size satellite and launch it into that more traditional LEO, and then it'll stay up there 10 years. But holy crap, I just spent a whole lot of time and a whole lot of money to get like this capability up there, but now I need it to last just as long because I spent all this time and money doing it. Whereas there should be some scaling where as you get closer down, you shrink the size, you shrink the cost, you get the same quality. So vis-a-vis, if that's the term, you should have a similar like value for that data. Now all of a sudden you kind of invert the cost time scale and you should be cranking these out and launching these up and getting just as much value out of the shorter time duration. But at like what point in the like 2 weeks to 2 months, or like can you come up with a technology like electric propulsion to keep you up there for more like a couple of years to pull as much value out of the new thing you've just built for way, way cheaper and way, way faster.
Was there a moment when you're like, did you approach this problem with like, it must be possible, figure it out? Or was there a moment where you're like, yeah, we know how to do this. Like this is going to work. Like how was that going through your head? Was that part of the early discussions? Like what?
Yeah.
How, like, I don't know, any sort of framework for approaching something of this scope?
I think jumping in, it was definitely like, yeah, we can figure this out. I mean, I've worked on so many different kind of missions, from school bus size satellites to the tiny CubeSats, where you seem like, and with like super crazy technology where you're like, this shouldn't seem like it should be possible, but the physics says it is. And then it turns out that you can do it. Yeah. So if this was just going to be, it felt a lot less than an engineering challenge and a lot more of like building a business behind it.
Did it seem counterintuitive? I mean, I guess because like as someone who's just at, I don't know, maybe you know things I don't, but it's like, it looks like very different. Like the punchline is like, it looks very different for any satellite you've ever seen. Yeah. Because it has to, because you can't have like things dangling out in the drag. Yeah. Right. And so it feels like almost like you were having to do some sort of first principles, like what is actually possible and like how do we build from there? Yeah, I think at the core of the way I always try to approach any problem, new or like previously solved or like kind of whatever, is that very much like a first principles approach, where you just say, what's the fundamental physics that says this is or is not possible? And then kind of building up your ideas of like, well, we could try this, and then assess that against the physics again. And then kind of develop your path around like how you're going to build this thing based on like those core fundamental principles. And like, what are the fundamental principles of this? Overcome drag, basically stay in orbit, one of our values. Stay in orbit, don't have this thing cost $1 billion. So make it like cheap, but in the right ways. But make it performant also. Like, can you build this super high resolution system, which has a lot of its own hard problems before you even get down into VLEO. And then can you blend all those together to come up with like a brand new way of doing something? Okay. I do want to get into the hard problems of the actual engineering and implementation, because I think that's like an interesting idiosyncrasy of this whole thing. Yeah. But first, like from a technical design perspective, was there ever a moment where you're like, maybe not? Like, or was it like kind of just like keep at it, keep designing it and figure out the problems one by one? Or were you ever like, how are we going to get through this? There's a wall here. Funny enough, there weren't very many walls. Instead there were like hard pivots in like the way we were approaching things, but those pivots were a little bit more centered around like the first principles, like fundamental physics that we were talking about. Like initially, our initial idea was like, oh yeah, it's like a significant high drag environment. We should be shaped like a bullet. And then I was like, this is stupid. How are we going to build this thing? Like, no one builds like this like submarine bullet looking thing in space. Like that would look crazy. Yeah, that looks crazy. No one builds that. And then you're like, okay, how do I make it reproducible? And how do I all this stuff? And I was like, no, that's dumb. Actually, let's go back and look at the physics of like what is causing that drag. How do you assess like how much fuel you need to bring? Okay, there's this thing called ballistic coefficient, which is the cross-sectional area times your coefficient of drag divided by the amount of mass that your system has. And you look at that term and you're like, well, what am I doing when I build this bullet-looking thing? I'm trying to reduce my overall cross-section, which is in your numerator. Well, there's two other terms in there that you should be looking at, right? There's your coefficient of drag. What does that mean? What is that actually made out of? And there's this heuristic out there that most satellites have like 2.3 to like 2.6 coefficient of drag without any association to like where those numbers come from. So can you dig into, oh, well, that's actually particle physics interacting with the surfaces and the materials on your satellite that are causing like momentum transfer as you're moving through the atmosphere. And what can you do about that material selection or those appendages or those crevices that you have at the most microscopic atomic level, and can you smooth those out in order to reduce your drag? And then you don't need to worry about cross-section as much. Or can you just like fucking muscle car it and throw a ton of mass at the system and just say, you know what, for
my incremental increase in area, I'm just going to 2, 3, 10x as much mass, because in the 21st century, mass doesn't cost as much because SpaceX has reduced launch costs so much. So let's take advantage of that. Stuff like that.
Yeah. I mean, there's like they're not anywhere as interesting, but there's like these mild analogs to like software. You're like, oh, the memory leaks, we should track that down, or just restart the server every 10 minutes. Like, it's fine. No one cares. like we have other stuff to do. So, all right. So you get through, you're like, all right, technically this pencils out. And then I guess I had a very big learning in watching the journey about the actual, I don't know, mechanics might be the wrong word, but like actually building things that you're going to shoot into space is like involves a lot of players and a lot of work, and like certainly like circles back on the math equations you just calculated. So I guess I'll start with like, did you know how to physically build it? Like, if you're like, you know, like how, like, was that like, okay, like I designed it, it makes sense. Mm-hmm. Like, did from your previous experiences, or you're like, all right, I know what's next. I know like who we need to talk to either build components or how we're going to build components on our own, or was that like a blank slate? Yeah.
So after the initial idea, there is like in the space industry, I'll say the space industry sometimes feels like a freaking Ponzi scheme, where like at every freaking layer of all the things that it takes to build a satellite, someone's like taxing the next person like an additional 10 to 30%. Like this is why space costs so much. It's just like this huge supply chain of people who are all trying to make a profit. And so you end up with multi-million-dollar systems that honestly, the core materials should not cost that much, but I digress. Understand, like trying to figure out where in that scheme you either make or you buy is pretty important, and like how you get to your eventual cost is also understanding like that make buy framework. So early on, you know, we have the idea, okay, this looks good, and then the company was founded on delivering data. And so while I'm an engineer at heart, I can also be fine like exporting some of the like design and build of like the system to suppliers. And so early on, we kind of initially thought that the best way to go about this was to basically buy a lot of the components. TLDR, it didn't end up that way. We're building a lot, pretty much all of it going forward. But at that initial phase, it was like, all right, we're going to go buy like a payload, which is like the telescope and optics part of it. And then we're going to go buy this satellite bus, which is kind of like all the brains and software behind it. But one thing we did always want to kind of make sure was ours was what's called guidance navigation control software, GNC. That's like the hardest problem about what we're doing. What's that putting? That's the hardest part of what we're doing is like how you actually control the system. I like to say what we are actually building is a space robot. Yeah. Like it needs to effectively like think for itself. It needs to control itself. It needs to know when we're trying to talk to it and talk back. And it's moving itself around in space to take these pictures. It's not like some satellites you throw up there and you just let them hang out and look at Earth and you just snap pics with like a selfie cam or something. Not us. We're like literally building something that turns, points, and like sweeps out this imagery. So
if only just because you're closer, and so like the range of view is tighter.
And it's way tighter. Yeah, you've got way less time over a certain like spot on the Earth in order to take that picture. And so you also want to like make sure your system is as capable as possible to take as many pictures as it can as it's like passing over this one spot on Earth. Like if we're flying over California, right? we want to take a picture of like LA, SF, and then like maybe within SF, you want to take a picture of Valley and Oakland. Like you got to move around quite a lot because you don't have a ton of data.
Which is like counterintuitive from the outside because you are selling images, but like the core IP is around fly, like actually how it flies.
How it flies, yeah. How it flies, how you coordinate and like orchestrate all the different like things that a satellite needs to do in order to take that like one picture.
And then, so in the first pass, when you're going out to vendors to buy components, did like their offering and talking to them heavily, like, did you have to circle back on the underlying physics and like the trade-offs and, like how much did it break your assumptions to learn what they could and could not deliver?
Yeah, it didn't break my assumption that we could do it. What it broke was my assumption that going and buying it from a supplier was the right way to do it. One of the early kind of conversations we had was, there's all these standard bus providers and like we should be able to just go out there and pick one off the street and then we'll impart our GNC software and it should be capable enough to do what we need, right? Not so much. Turns out that when you build something fairly common and like ubiquitous, you also lose a lot of the like capability that comes along with building something specific for one task. Sometimes I like to think about it as the difference between like Python or C++, where like if you're trying to get as much hardware performance as possible, getting as close to like the actual assembly language is better versus the abstraction helps be a general great tool for a lot of different things, but maybe not fully optimized for like your specific problem. And so going to these standard bus providers, like they're great for a lot of different things, but as we tried to be like, okay, we need you to do XYZ performance, like timing is a huge thing for like super high resolution imaging mission. And they hadn't really orchestrated their flight software system to be able to understand the timing discrepancies and like the timing jitter within their commanding and executables. And so all of a sudden it looks like our mission's totally broke, but it's not. It's like, well, we're telling them, well, why don't you do this? Why don't you add this code in here so you can understand like how much latency is being introduced at each one of these steps as you're going from sensing to like computing all the different things you need to do to commanding your actuation system. And they're like, it's just like a little bit of deer in headlights. And you're like, well, why am I teaching you how to do this thing when I know how to do it and I can just go find people to come aboard and build this with me and do it ourselves?
Cool. And then you made that decision and you had, like, it was hard. Like, I don't know, how hard a call was that? How would you think about it? Like, were you, how confident were you? Was it a borderline? Were you like emphatically?
Yeah, I think like one of the key things.
So the decision being to take the bus manufacturing
in-house. Yeah. One of the key things I've learned as a founder, been doing this like 5 years now, is a lot of these key kind of pivotal moments in the company where it's really easy to fall into the like fear-based decision-making framework or to decide that I'm just really tired and I don't want to do this. We had actually debated like kind of twice prior to bringing the bus in-house whether we should do it. The first one was early on, like I was saying, when we were just getting started, where it's like, oh, there's these common bus providers, let's just do it. And I like, in my heart of hearts, really wanted to do it ourselves, but I was like, okay, yeah, it's probably easier. Like that sounds like the easy way out. Second time, I was actually in Sausalito working remote, and we had been debating, Topher and I had been debating for like 2 months whether we should do it in-house or like go with this proposal we had gotten from this bus provider. And like the proposal looked like they had all the right things, and like from a cost perspective in terms of like upfront cost, it was going to be way cheaper than hiring a ton of people. And like, but I just like something felt off about it, and we had just debated and debated and debated. And I could tell like the day we decided, just he and I were so sick of debating it that we went with the easy option because it was less scary and it like looked fine on paper. But it was a different fear, a fear of this like not working that made me be like, oh shit, like we made the wrong call. And like, now I need to like, let's actually think through, let's analyze like how hard it would be to hire all these people. What's the schedule? What's the cost? Like, let's actually put the work in to figure out if we can do this ourselves. And then from there, it wasn't a fear-based decision. It was one made in confidence, saying that I know we can hire these people because I have this network. I know exactly how much it's going to cost because I've done all the cost exercises. And like the physics is something we've already been teaching to them how to do. And so from like that point forward, like making sure I'm never making a decision based in fear has been something I've leaned on like countless times. And there's been a couple other times where it's popped up and I have made that fear-based decision and it's always the wrong one every single time. So there's been no regrets since making it ourselves. And it's honestly been like one of the greatest decisions we've ever made in the company.
Yeah. I mean, there's so many threads there. Cause like, first of all, it's like, you're already so risk on doing a startup, building a space startup that builds novel satellites and no one's done. And so like the appetite to like burn down any like risk you can like or control for like makes perfect sense. But the flip side is like you don't do things no one's ever done before by like ceding control to people you don't trust. Right? like you want the ball. Like that's why you're here in the first place. Like the entire point is to be risk on. So it is a very hard and like it is interesting because you don't get it's like a matter of number of shots, right? Like it's like you're kind of making you're almost making like an expected value bet. You know what I mean? Like it's not one part of your head is like, what is the how do we make sure we don't fail? And the other part is like, what if it works? And like controlling all that IP and building all that stuff and having that as a core competency, like it's like what you actually want.
Yeah, it's been fun. I guess is one way to put it. But like that, I go back to like that make buy, like I was saying early on. And like over these like I had one at Lockheed, they have these like make buy trades and make buy framework. I always felt dumb. But having to like make that decision so many times of like, what do you take the risk on? Like, what is the expected value? What is it worth taking the risk on? Like changing the entire game, and like, what kind of capability do you have to either do it yourself or go and find and attract the people who are going to help you figure out how to do that. And so I have actually built out my own kind of framework. It's like this cube of like how we've been assessing as we continue to go down building satellites and like deciding what to bring in house versus like exporting and like just gonna let somebody else build this for us and like we'll buy it. But like I've got like 3 sides on this cube. One is like strategic importance, and like I think that falls in squarely like, what is the thing that you're going to do that's going to change the world, and like how important to like your company existing and beating everybody else and owning the industry is that? You should obviously probably be building that, right? It's not like, oh, we're going to figure out how to like build 10 centimeter imagery and then we're just going to export everything about how to do that and like hope we build a company off of it.
Because in that case, like it's a good answer that it's risky and hard.
Yeah.
Because if you get through the other end, it's much more valuable.
Yeah. And to your point, it might be more immediately obvious.
Well, there's also this weird thing where you need to have a pretty heavy degree of situational awareness around the vendors and the ecosystem, right? And like there's an interplay between like they could do it if it was relatively commodity, right? But if it was relatively commodity, there's no point. And like that being a key part of what you're building, right? And so there's like this interesting analysis there.
Yeah, and like the space industry is not large either, but of the players, they're like huge defense contractors, right? Where if it was like if there was a ton of money to be made and like they had all the expertise, they would just like do it.
There's
right?
this whole second aspect here that's idiosyncratic to space about the incentives of the people you're paying, especially as they relate to small startups.
And like, honestly, that kind of played into the bus trade too. Is like, if I'm starting to teach this company who could potentially just take a lot of our like IP behind this and then go and build a similar system, like, what the fuck am I doing? Like, I'm just like teaching myself out of.
So we don't have
the
we don't
company.
have the experience, and now they do. It's
Yeah.
like, and we help them get there. All right, maybe like. I don't. It might be just like some specific anecdotes of stuff you got through in the engineering process. I don't know what, like maybe the mirror saga.
Yeah.
We can go into it for a bit.
Yeah.
It's kind of instructive.
So, yeah, hit me up again in 5 years. We'll see if I solve one aspect of this problem. But like these big mirrors, and like when we build like a payload, which is an optical telescope, same as like very similar to a telescope that like sits on the ground. You've got this big tube, and if you look down the tube, there's like a big mirror at the bottom, and while you're looking down the tube, there's something kind of in the way. That's the secondary mirror. The big one's the primary mirror. And then the way it works is light is traveling down the tube, bounces off. That primary mirror is focused onto the secondary mirror. The secondary mirror then bounces it down the optical train into whatever back-end optics you have. Typically, there's like a tertiary mirror or whatever. But like the hardest part of that is the big mirror, right? The primary mirror at the bottom. So for us, with a very big satellite, that mirror is huge. It's not 2 meters across. Like Hubble's mirror is like 2.5 meters, which is like, what is that? 6-7 feet in diameter. That's a big mirror. And what that means, ours isn't that big. It's scaled like in half, a little less, but it takes a long time to, one, kind of form that mirror. And by form, it's like, it's not just flat, it's curved, right? I said it was focusing light onto the secondary mirror. So you've got a very like fine shape to it. And glass is super heavy. I don't know if you've ever picked up like a huge chunk of glass, but it's hella heavy. While mass like plays in our favor, you typically don't want like a ton of mass where you don't necessarily need it. And so there's a lot of light weighting that goes into that mirror. You basically like kind of bore out the back of it.
Mass play in your favor because even though it costs more to send up there, once it's in motion around the Earth, it wants to stay.
Yeah, for the ballistic coefficient. But like when you're designing your system, so another hard part of what we do, like I said, this satellite's like moving around a lot. That means like if you've got mass at kind of like an unideal place compared to your center of mass, you increase your inertia. And so if you have a ton of inertia, you're trying to move at once, then your agility gets a little bit harder.
All right, back to what you're saying.
So we're building this mirror. It's a big chunk of glass. You got to make it real smooth and in a specific shape. You're trying to lightweight it. And then you're doing like final finishing where this is very specific kind of glass that is kind of built to be polished down to like nanometer level precision. The same width of your hair is how like smooth it needs to be. So all that to describe that it takes like frickin' 12 months to build one of these things. It's stupid. I hate it.
Yeah. Which is like a problem. Generally, there's like this long lead
huge
time item that's like a whole different bucket of complexity of building these systems.
I mean, going back to whether this is possible, the first quote we got from our supplier of this like initial telescope was like 2 years. And we're like, what the fuck? Like we could do so much in 2 years. But anyway, the majority of that time is building that mirror. And so it's going through this whole fabrication process. And we're like, I don't know, like 7 months into the schedule. And we're at the point where we're lightweighting it. And so to lightweight glass is a little bit different than metal, where for metal, you could just like take a CNC machine and like bore it out and you'll be fine. Yeah. But metal's a little bit more forgiving compared to glass, which is very brittle. And so there's only a couple ways you can lightweight, one of them being taking water and just shooting it at the glass as fast as possible. And it's called a water jet. And so you like slowly wear away at the glass. But in order to do that and still not break the glass, because it's still glass, you have to have these very specific like settings and like nozzles on the water jet and all this stuff. And 7 months in, one of the techs like was changing out parts and like forgot one of the parts and just like turned on the machine and huge hole in the middle of our freaking massive mirror. And we're just like, oh my God, like we only have one, because they're also crazy expensive because they take so long. And I'm like, great. Like, what are we going to do? Like, are we just set back 7 months that we're going to have to like find additional runway and stuff?
And the vendor's reaction was just kind of like,
oh yeah, this happens all the time. Yeah. Process escapements. Yeah, it's totally normal. We break mirrors all the time. I'm like, what the fuck do you mean you break mirrors all the time? Your whole job is to build mirrors. Like, should be like fairly obvious at this point. Like,
they take 12 months.
The things that you need to do versus not. Yeah, and they take 12 months. They're like, oh yeah, it's just another one. Yeah. What do you expect? Yeah. They were so nonchalant about it, and it was kind of annoying. But yeah, so we're like, okay.
But that made it like emphatically your problem.
Yeah, on like,
even though you were paying someone to do it for you.
Yeah, well, and of course we're going to need to pay them to fix whatever they already screwed up, because that's how space works. You pay the people who screwed things up to fix the problems they made. But yeah, so you have this like very nice looking piece of glass with a huge hole in it, and there's like a couple different ways you can deal with problems like these. One is to build a whole new one, which we didn't necessarily have time for. The other is for this like specific way that we were building this mirror, is you can take a smaller chunk of glass and like refuse it into the other one, and then just make sure that the location that you do it gets the appropriate treatments, and then like is refinished kind of in the same way, where you're not inducing additional stress in the rest of the mirror or stress in the section that you had, but basically acts like a Band-Aid and fuse it in there, and then keep going. So
was that on like, did you intuit that was an option, or did the vendor know, or did you have to like go like, what was the process of actually like?
The vendor did know. It hadn't been done on one with this size, and there was some different like material things that we had to go into around like the type of glass, and like there's also, when this happened, there's a whole supply chain thing of like, okay, we have a engineering solution, but how do you actually like get the material in order to do it? And
you're like someone was like physically on site with them basically at this point.
Yeah. So, yeah. Had to go out there, and like also because we're just like a startup and like this is a pretty big contractor, like not also the top priority, especially when they're like, oh yeah, this happens all the time. Sorry. Yeah. So there's a whole game that ensued of figuring out what the like engineering solution is. Like, okay, we're gonna like take a smaller chunk of glass and like fuse it in here, and then flying out there to like yell at some VPs about priorities and like, why did you break my glass, and like getting them to not be so nonchalant about like, oh yeah, this happens every day, and then like a pretty good supply chain game of like going to the various glass suppliers, but also like going to the other programs that they were working on, the other customers, and kind of being like, hey, do you guys mind if we like take this chunk of glass? And we ended up finding some, I think maybe from some other program. I don't want to bring it up here, but some other program that got canceled there. And so they weren't using it. And so we had to do this like whole contracting transfer while also like sitting out there on the supplier and also making sure like what the hell happened this first time, where are your like process escapements, and like it ends up being this whole engineering plus program management plus supply chain plus like we ended up having to pay them in order to fix it, to try and like save what could have been like any other, like if I was still at Lockheed and that happened, the program would have slipped a year. Like by far, we lost no time to our like eventual launch schedule because we solved this in like 2.5 weeks. So it was a little bit of a hellish, like all hands on deck, some long nights and weekends, but was able to recover it and kept the process going.
Yeah, I mean that's all. I mean that's awesome. I guess it's also just the roller coaster. It's kind of never ending. Do you feel like you have learnings other than more of the same? You know, we want more control of things in house, or like other. You know, I don't know. What else are your takeaways?
One is like knowing your supply chain as best as possible, and like just having as many options open as you can. One term I throw around to the team quite a lot is like playing 4D chess. A lot of times you need to think not just in like what are my moves that I can make in like going the direct path, like going to my supplier and saying this is your problem, fix it, but like also being like, can I rewind time in any way, shape, or fashion to like fix this in a pretty novel way, maybe come up with a different avenue of attack that isn't just like hitting the problem head on. Like that one is like, finding a new chunk of glass to fit in the middle, pretend like it didn't happen. And then like just always having a couple options out there too. Like we could have just assumed that this was our problem to solve, and then we had to go like to a vendor, or like we were supposed to have spares ready to go. Like that could have been an option. But instead we're like, this is a big contractor. Someone else here probably has this glass that we need and can probably make it immediately available. Yeah. And so you're going kind of out of the box and be like, yeah, can we snag that from you? And we'll like maybe pay for it later. So yeah, playing like 4D chess is kind of, no matter, every time I hit one of these problems, it's like, all right, never just think about the head-on solution. Another time is like for our propulsion tanks, we got them in, and then we got like the spec from the vendor, and the tanks on the spec, I forget if it was on the spec or like talking to the vendor, but they're like, yeah, when you pressurize these, they like change in shape. And you're like, this is like a pressurized vessel. Like, what do you mean it changes in shape? And they're like, yeah, you pressurize it and it like gets bigger, it expands. And we're like, this is supposed to go to like thousands of PSI. Like it's a bomb. What do you mean it changes shape? That doesn't sound structurally sound. And my principal mechanical architect, he could not comprehend this. He's like, what dumbass fucking design is this? But we found this out with like 4 months until we were supposed to ship to the launch site. And we're like, well, fuck, what do we do? So I'm like, all right, look if there's anywhere in the local area that supplies tanks who might just have like something on stock. And so we just like start calling all these local shops. And one of them's like, oh, we've got like one couple just like sitting over here. We probably get it to you in like a week. And I was like, damn, how much? And they're like, I don't know, like $5,000. I was like, $5,000? Bye. So we just like changed this aspect of our design with like 4 months to go. And like, it was pretty, if it was a larger impact, like this is a structural thing, it's pretty easy. If it was a larger impact, maybe a little bit more time, but it's just like making quick moves like that whenever you hit a problem, knowing that the immediate, like, I need to solve this specific thing isn't always like the best path.
Yeah. Yeah. Well, also I just like the thinking ahead, like there's like a level of adversarial thinking about what might go wrong, and inclusive of like, you know, in both these examples, you're kind of like, we just assumed that what we asked for is what we were going to get. Like it would have been fine. But like the scope in these like bespoke space builds is everything. Like everything is now, if you're going to send it into space, it is in your specific purview to ensure that it like gets into the spacecraft perfectly.
Yeah. That's kind of the fun, like, honestly, no other job do you need to worry about everything. And like, it's stressful.
It ties back to like writing assembly analogy, right? Like you just like, like if you don't know exactly how everything works, then there's any abstraction is terrifying.
Yeah, get out of the game. It's part of the fun. Being able to go down and like, that's how you pull out performance, right? You don't just know one aspect and then like leave the rest to chance. No, you know everything you can about everything about your system in order to tweak the knobs in the right places in order to do like the incredible, something that's never been done. And that's the only way. Like you need to know everything.
You need to know. Well, at that, like, sweet. This has been awesome. Thanks so much for spending time with me. This has been fascinating. Anything we should be looking forward to from Albedo?
Yeah. So we just launched a couple months ago. We are trending our way down to VLEO from LEO because SpaceX doesn't quite yet drop off right at VLEO. But within like the next month or two, we should have first light, which is our very first pictures of those 10 centimeter images. So
yeah, that's going to be so awesome. Awesome. Yeah. Thanks so much.
Thanks, Brett.
All right.